Hey guys, this is Shayan. Today I'm gonna solve another 2000 plus difficulty DP problem. Again, I have to mention that don't forget about this spreadsheet. In here you can see all the problems, and in front of each problem you can see their videos if they're being uploaded. And whenever you solve a problem, you can just write solve in front of it and everything will be updated. So if you want, you can make a copy out of it and have your own version and use that. Okay, let's talk about this problem, another MEX problem, 1870E. In order to understand this problem, the first thing that you need to know is definition of MEX. Well, MEX means the smallest non-negative integer that is not in a list. For example, MEX of 0, 3, 4, 7, 2, is 1, because the smallest non-negative integer that is not in this list is 1. MEX of 1, 2, 3, 4 is 0, because 0 is not in our list. The 0 is the smallest non-negative number that is not in our list. And MEX of, for example, 7, 1, 4, 0, 2 is 3. Okay, because 3 is the smallest non-negative integer that is not in this list, and so forth. So in this problem, you have an array of n elements. N is up to 5,000, and AIs are up to n as well. So you have this array A1, A2 to AN. You want to choose several sub-arrays from this array. Each sub-array is a continuous interval of the array you have. So you want to choose several intervals of this array in a way that each element will be in at most one sub-array. So each of your elements should be in at most one of these sub-arrays, such that at the end, when you calculate MEX of each of these sub-arrays, for example, M1, M2, and M3. And as I said, some elements can be in none of the sub-arrays, but the sub-arrays should not overlap with each other. Okay. At the end, you want to maximize the value of M1 bitwise XOR of M2, M3, and so on to, for example, if there are K of them, to MK. So you want to, at the end, maximize the value of bitwise XOR of all these values. You can see the link of this problem in the descriptions below. Try to think about it, and whenever you feel stuck, continue watching the video. Okay guys, the first thing that I want to say is that we want to discuss an O of n cubed solution. This is the first step to solve this problem, and then we try to gradually improve our solution and make it faster using several facts. So we're gonna use several facts at the end to improve O of n cubed to a better solution. But for now, let's talk about O of n cubed. Well, for O of n cubed, I can have some dp of I and j such that it just means that I considered only the first I elements, and I had several intervals, and because the number of intervals are not important, I had several intervals, and the XOR of MEXes of them is gonna be j. Okay, so XOR of the MEXes is gonna be j, and I'm only considering the first I elements. Well, obviously dp of I and j can go to dp of I plus 1 and j, because I can just ignore the next elements, and whatever I had till now I can have for the first I plus 1 elements as well. But also I can say that when I want to see that which dp of I and j can update, I can also consider the case where I plus 1 is important and is in some subarray. So till now I have everything in the first I elements. Now I'm starting from element number I plus 1. Okay, so now I'm considering the case where I plus 1 is also in a subarray. So what I can say is that it will start from here and go to somewhere. For example, goes to index L. Because I'm considering that right now I have the answer for the first I elements, and this is the answer for now. I just solved for the first I independently. Now I want to consider the case that from this next element I start a subarray. So it's like each time from the start of each of our subarrays we will just consider those cases and update the next values of DPs. So what do I mean? As I said, if I have already solved it for the first I elements, I either ignore the next element or I start another interval from there. If I start another interval from I plus 1 to L, I need to find out what is the MEX of the values here. And in order to calculate that with a good time complexity, I can just say that I can, each time when I increase L, I can initially say that CNT of A of L plus plus, and then I can say that while CNT of MEX was non-zero, I can write it like this, MEX plus plus. So this way I can just say that increase A of L, and while the CNT of MEX was not zero, that means that I have at least one of that value. So I can just increase MEX by 1. This way, in total, when I start from some value and I go forward, I'm sure that my MEX will be just added by 1 at most n times, because MEX cannot be greater than n. So in total, my time complexity for calculating the MEX in all the subarrays wouldn't be bad. Okay, and then when I'm on some L, I can say that from dp of I and j, I can go to dp of, for example, L and j XOR the current value of MEX. Okay, and this way I can say that, for example, if I and j was possible, for example, I can use the first I elements and partition them in a way that it is possible to have XOR equal to j, then this is possible as well. So our DPs are kind of just booleans. They can just be true or false. I mean, can we make this or not? So this way we can update them, and in total I can find these DPs in O of n cubed, and at the end find the greatest value x such that dp of n and x is 2. And that's gonna be my answer. Now think a little bit about how we can improve it to a better time complexity. Try to find some facts. Using some facts you can improve this solution. Okay, here I want to improve my solution. What can I do? Well, maybe the first thing that comes to my mind is gonna be if I can somehow find a way to limit the number of intervals that I can use. You know what I'm talking about. For example, if I have considered right now, I have considered n squared intervals, and I have considered, okay, they are one of my intervals that they will be added, and their MEX is gonna be equal to the current MEX that I have in my variable, and I have considered the case that I'm gonna add them. But now what if I can somehow just consider very fewer number of interval and just work with them instead of working with all the possible intervals? So is there any fact that I can say that, for example, if an interval has some situation, then definitely I will not use that in my answer. So there is an optimal answer that will not use this interval, and I can get rid of this interval easily. Is there any fact that we can say so that we can get rid of some intervals? Think a little bit about this. Well, what we can say is that for the intervals, like for example L1 and R1, and assume that there is another interval inside it, L2 and R2, completely inside it. So L2 is greater than or equal to L1, and R2 is less than or equal to R1. Pair of L2 and R2 is different to the pair of L1 and R1. If their MEXs are equal, if both of them, for example, MEX of this one is M, MEX of this one is also M, then I can say that I will never use the interval from L1 to R1. I will never use it. Why? Because if I'm gonna use that, instead of that, I can use this smaller interval, L2 and R2, and then I have more elements free to join the other intervals. So it doesn't make sense to use this interval anymore. Okay, so I'm saying that if I have an interval and inside that I have another interval with the same MEX, it doesn't make sense to use that bigger interval. So now try to find out that if we get rid of those intervals like L1 and R1, then how many intervals will be left? Okay, I want you to prove that the number of intervals will be at most 2n. Try to prove that. Consider all of those intervals that remain at the end. For example, they are from some L to some R. This value is A of L. This value is A of R. One of these two is greater than the other one. Because obviously, if they are equal, then we can eliminate one of them and the MEX does not change. So this subarray is not a good subarray. So one of them is greater than the other one. Assume that A of L is greater than A of R without loss of generality. Then what can I say? If A of L is greater than A of R, I can say that this is the only interval that L is in the left part of it, and A of L is greater than A of R. So there is only one subarray that L is to the left of it, A of L is greater than A of R, and this is a good array. Try to prove this. This is gonna be simple. So just try to think to prove this. If you prove this, then you can easily show that the number of intervals will be 2n at most. Okay, what can I say in here? A of L is greater than A of R. So now consider that there are two such intervals. Two intervals that both start from A of L. For example, one of them is this, one of them is this. Both of them start, for example, this one goes from L to R1. This one goes from L to R2. And A of L is greater than or equal to A of R1, and also A of L is greater than or equal to A of R2. And both of them are good. I'm gonna show that it is not possible. Consider that R1 is less than R2, for example, the first one is the shorter one, for example. There's no difference, right? If that happens, I can say that it is impossible that A of R2 is useful. Why? Because I already know that if L is useful, if L is not useful, then this is a contradiction, because I could remove L from here and still my MEX wouldn't change. So it is impossible that L was not useful. Definitely MEX here should be greater than L. A of L, I mean. Because otherwise, if MEX is less than A of L, it cannot be equal to A of L because I have A of L. If MEX is less than A of L, then I could easily remove this one and MEX wouldn't change, which is a contradiction because it shows that this interval was not a good interval. So now I consider that MEX is greater than A of L. So this one was useful, and it means that we have all the numbers from 0 to A of L already. So having A of R2, which is less than or equal to A of L, is not useful anymore. As I said, it is also strictly less than A of L. Both of them are strictly less than. There's no difference. Both of them is obvious that in both of the cases, it is a contradiction, because if A of R2 is less than A of L, we are sure that in here we have A of R2 already. So I can remove this, which is a contradiction that shows that we cannot have two good intervals such that both of them start from this L, and in both of them A of L is greater than A of R. So as I said, I have two type of intervals. Either A of L is greater than A of R, which, as I said, there is at most one such interval starting from each point. From each cell, there is at most one interval that's in one such interval that starts from there. So it's going to be at most n such intervals, or at most n such subarrays. If A of R is greater than A of L, then I can say the same thing for the right part of each subarray. I can say that for each cell, there is only one subarray such that this one is the rightmost element of that. Because again, if there are two, I can say that in the first one, R was useful, so I have all the elements from 0 to A of R. So A of L2 is not going to be useful for me because it's less than A of R. And I already have all those numbers in here, so that is not useful, so I can remove that, which is a contradiction. And shows that the second interval was not a good interval. So there is at most n of these intervals as well. So there are at most 2n good intervals. And that's all. So when I know that there is at most 2n intervals, my DP can be only on those intervals. Okay, so now we know that we have at most 2n intervals. How can we find those intervals? Feel free to pause the video and think about that if you want, but I just continue. So I start from each A of L. Assume that I want to first find all the intervals like this. Let's say A of L is greater than A of R. And the other case is very similar to this. I start from each element, and it's enough to consider the first time that my MEX is gonna be greater than or equal to L. I mean A of L, definitely. It's enough to consider the first time that my MEX is greater than or equal to A of L. If I consider there, it is impossible that there is another good interval such that the rightmost element of that is less than A of L, because I already have those elements, so that never happens. This way I can find all such good intervals, and the case where A of R is greater than A of L is very same. So that's gonna be all about finding the intervals, and then when I know the intervals, I'm gonna just use them. Each time, as I said, I still have this transition from dp of I and j to dp of I plus 1 and j. I still have this transition. But this time, instead of having another 4 that starts from I plus 1 and goes to all of the intervals, it's like I have a vector this time, and in this vector I keep all the good intervals. And then I just have a 4 on those good intervals that start from here, not all the intervals that start from here. And this way, in total, I will have a 4 on at most 2n intervals. And this way, I can update several values such that in total, my values of L is not gonna be n each time. It's gonna be n in total. So in total, my solution is gonna be O of n squared. And because n is at most 5,000, this will work. And this is gonna give you the solution. So the general idea behind this problem was that first, it's easy to come up with an O of n cubed solution. So we come up with this solution. And then we say that how can we improve it? There are several paths to improve this solution. And we should think about all of them. We should explore all the different ideas. But one important idea that can come to your mind is that what if, when I have this dp of I and j, it is very intuitive to think about dp of I and j. I do not update all the possible intervals. What if I can just update a small number of intervals instead of trying to update all the possible intervals? And then you can start thinking with this idea that how many intervals I should consider. Okay, so a good path to solve this problem is like this. dp of I and j is very intuitive, and this initially gives you an O of n cubed solution. And in order to try to improve it, you can just think about what if I don't have a 4 on all the possible intervals, but only on some specific good intervals instead. And this way you can come up with the fact that there are at most 2n good intervals, 2n important intervals, and I can just consider them as the possible intervals or subarrays that I'm gonna have at the end. Guys, I try to upload these videos every Thursday, but the important thing for me is to make sure that this is beneficial for you. So make sure to tell me about your opinion about these videos. You can say that in the comments below or send me a message in LinkedIn, in Instagram, in Discord, wherever you want. Just let me know that how do you feel about it, and is there anything that I can improve it to make it better or not. Your opinion matters a lot for these videos because these videos are made for you. Thank you very much.